Let's talk about parametric curves. We would like to be able to describe curves that are not functions, okay? So if you take a look at these two graphs that we have over here, uh, on the left side, we have a very familiar object. This is a circle. We can see this is not a function because it fails the vertical line test. And we know even more about this circle. This is something we call the unit circle because the radius of this circle is 1. So this is an example of something called a parametric curve. Let's take a look at this example in orange here. So in this example, you got this weird infinity looking symbol. This one also fails the vertical line test, so it's not a function, but it's still a curve that we can still work with. And this would be another example of a parametric curve. I want to move to the next page real quick. If you look at this purple graph over here, we have yet another example of a parametric curve. Again, this fails to be a function because it's going to fail the vertical line test. Okay, so this third curve is a little bit different from the other two because the other two curves are like closed loops, whereas this one definitely has like a beginning point here and an ending point here. So we'll get back to describing this situation in a little bit. All right. Now, even though these objects are not functions, it still makes sense to talk about the tangent line to the curve at a point. But we're going to need to be able to describe our curve a little bit differently. All right. So instead of having a single equation to describe the curve, we're actually going to have two different functions, one for x and one for y, that will describe this curve. And these two functions are called coordinate functions. All right. Now, in the past, x was considered the independent variable, and y was considered the dependent variable. So the question becomes, when you're working with a parametric curve, which one is the independent variable now? And the answer to this question is neither is the independent variable. So what makes a parametric equation is that we're going to introduce a new variable t into our situation. And this new variable t is called a parameter. Okay. So frequently we think of it as representing time. So one of the reasons why we like to use t for our parameter is that it represents time. So I want to go back to the top of the page and take a look at our first two curves over here. Okay. So when you look at this purple curve, when you think about this, you can write down an equation for it. So we know that the equation for it looks like this. You can write that as x squared plus y squared is equal to 1, right? We know that we can write equations of circles like this. However, the way that we're going to write it in parametric form is going to be a little bit different. So we're going to have two equations, x equal to something and y equal to something. And these two equations are going to depend on t. So maybe what I should have done is I should have, instead of saying x equal to something and y equal to something, I could say x of some variable and y of some variable is equal to something like this. And to be honest, you've actually already seen uh, an example of a parametric curve. Because if you think about how did we describe different points on the unit circle when we were talking about trigonometry? Well, we really measured an angle theta from the positive x-axis, right? So in the past, you saw stuff like cosine of theta representing x and sine of theta representing y. And what in order to trace out the full circle, you would have to let theta range from 0 to 2 pi. So maybe we could put a restriction like theta is going to be between 0 and 2 pi, like that. And if we did it this way, then you would have a theta here and a theta here. This is a parameterization of a circle that you have seen before in basic trigonometry. Now, it's totally fine to have your parameter be theta, but a lot of times what we're going to do is we're going to let our parameter be equal to t. Let's look at the graph on the right side here. This is some sort of a thing that looks like infinity. So this may or may not have a nice, what we call closed form solution, or a nice equation in terms of x and y that describes it. But I know for sure we can describe this curve using parametric equations. So this curve right here has the following parametric equations. X of t is going to be equal to 2 cosine of 2 pi t, and y of t is equal to sine of 4 pi t. And again, for this guy, t is ranging from 0 to 2 pi, like this. Okay. So one of the things that's interesting about each of these examples is that their starting point and their ending point are the same. So if we go back to our circle example, when you plug in a 0 in for theta, you're going to get the point 1, 0. And then as theta changes, it's going around in this direction like this. And then when you get to the very last point, when you plug in a 2 pi, cosine of 2 pi and sine of 2 pi, that takes you back to your starting point like this. So one of the cool things about a parametric equation is that it actually has a direction associated with it. Whereas when we write it in Cartesian coordinates, there is no direction. So sometimes when you want to indicate the direction, you put little arrows. So we have a little arrow going like this. This kind of describes the direction the curve is going. All right. If we looked at our infinity symbol looking thing, our starting point is going to be 2, 0 this time. You're going to trace it all the way around. Your ending point is going to be the same as your starting point here, which is 2, 0 again. If we wanted to, we could put arrows to describe the direction. You know, it goes this way, then up, then down, like this, and then back up to the starting point. So we will look at examples in class, more examples in class when we meet in person. Let us take a look at that graph at the bottom over here. When we look at this curve does not have the same starting point and ending point. So I created this curve in Desmos, and I can tell you what the parametric equations are. X was equal to, we don't always put the of t there. I think it's nice to indicate the dependence on t, but sometimes people just write x equal to t squared minus 3, and we could say y is equal to 2t plus 1. And in this particular example, I had t ranging from -2 to 3. Okay, so in general, if you have your x of t is f of t and your y of t is g of t, and t is ranging from a to b, then when you plug in an a, which is the smaller value of t, we call that the initial point. And when we have um, f of b, g of b, that's called the terminal point. So the word terminal means something ends. So like when you fly at an airport, you land at the terminal, that means that's the end of that leg of the trip. Or if you have a terminal disease, that means you're nearing the end of your life. Okay. So I just wanted to reiterate one final thing. Even though we have these parametric curves, we can still talk about tangent lines to the curves, right? Like I could come over here, I could say, oh, we have a tangent line at this point right here. That tangent line looks like this. And I can find a slope. Or, oh, we might have a point right here. I can find the equation of the tangent line right here, like that. So we are going to eventually perform calculus on parametric curves, but this video just tries to introduce the basics of parametric curves. All right, everybody. We'll look at more examples in class later. Take care.